for neutrons of one speed to derive a, so diffusion equation can be obtained by integrating transport equation. So Fick's law can be obtained by considering conservation of neutrons. Then this will be combined with the conservation equation for neutrons of one speed to derive a useful form of the diffusion equation. For this, we have to recollect the earlier which I have told, and the condition of continuity, and second is Fick's law of diffusion in the context of string. And some near point R. So all the neutrons are the same. The velocity would be same. Form of I top the rapture or some may escape from the volume V and some others may enter it. So there may be a leakage and there may be an incoming neutron flux. Also, if neutron sources are present within the volume, additional neutrons may appear from these sources. At any time, the neutrons within this volume satisfy the condition of continuity. This means that the time rate of change of total number of neutrons in volume capital V must be equal to the rate at which neutrons are produced within volume V minus the rate at which they are either absorbed or escaped. If n, which is a function of position vector and time, is the neutron density at r vector and time t, the total number of neutrons in volume V is given by integration over the volume n r comma t dv. The condition of continuity can be written as d by dt integration over the volume n dv, which is equal to production rate subtracted by absorption rate minus and leakage. Production rate minus absorption rate minus leakage. So production rate can be derived by using the formula integration over the volume S dv, where the source distribution function S is a function of R and T. Similarly, the absorption rate can be estimated by using the formula integration over the volume summation sigma A phi dv, where sigma A is the space dependent absorption cross section. Similarly, the leakage rate can be estimated using the formula integration over area J vector n cap dA, where J vector is the neutron current density vector, which is a function of position vector and time, and n cap is a unit normal to the specific bounding. Like absorption rate, leakage rate is also a negative term, as it signifies loss of neutron. So you can summarize d by dt integration over the volume n dv is equal to integration over the volume s dv minus integration over the volume sigma a phi dv minus integration over the area surrounding the volume J vector n cap dA. So we can use Gauss divergence theorem and transform the leakage term from a surface integral to a volume integral. So integration over a j n cap j dot n cap dA is equal to integration over the volume divergence of j dV. Note that all integrals now involve volume integration, and hence the integrands on both sides must necessarily be equal. So you can write dN by dt is equal to S minus sigma A minus divergence of V, divergence of J. So this is the equation of continuity, and it carries huge significance in reactor theory. When the flux, current, and sources are all independent of time, the term on the left-hand side will drop, and the system is said to be in steady state. So your original equation is now reduced to divergence of J plus sigma A phi minus S is equal to 0. So neutron density and flux are independent of position, and we can choose divergence of J is equal to 0. Now the original equation will become dN by dt is equal to S minus sigma A phi t. So we can summarize that your one speed neutrons are conserved, and your production rate minus absorption rate minus leakage rate is nothing but derivative of dt integration over the volume n dv. Okay, so neutron transport is a complicated phenomena, and under certain conditions neutron flux phi and current j vector can be related in a simple way, which is identical in form to Fick's law. Fick's law is used to describe diffusion phenomena in liquids and gases rather well, and use of Fick's law in reactor theory leads to what is known as diffusion approximation. Under certain simplifying assumptions related to neutron current density at any point in a medium containing neutrons, Fick's law can be derived by making the following assumptions. The medium is infinite and uniform so that all cross sections are independent of position, and there is no neutron sources in the medium. Scattering is isotropic in the laboratory coordinate system, and the neutron flux is slowly varying function of position and independent of time. So you can have your Fick's law in a schematic diagram as shown in the slide. The current density J vector, which can be resolved J vector, which can be resolved into Jx, Jy, and Jz, is calculated at the center of coordinate system. For evaluating Jz, the Z component of J, we can consider the rate at which neutrons flow through area dAz in the xy plane at the origin. Since we have assumed that no neutron sources are present in the medium, every neutron passing through dAz would have arrived from a scattering collision. Neutrons flow downward through dAz as a result of collisions above xy plane and flow upward through dAz from collisions below the xy plane. If sigma s is the macroscopic scattering cross section and phi is the neutron flux at position vector r, then the number of scattering collisions that occur per second in the volume element dV located at point r vector is given by sigma s phi r dV. If scattering is assumed to be isotropic in laboratory system, the fraction of these neutrons scattered in the direction of dAz is just equal to the fraction of total solid angle subtended by dAz at dV. From the definition of solid angle, this fraction is nothing but dAz cos theta by 4 pi r square. And the number of neutrons scattered for second in dV which head toward dAz is sigma s phi cos theta dAz dV by 4 pi r square. But all these neutrons do not reach dAz. Some are scattered or absorbed en route. Keeping this fact in mind, we can write the number of neutrons reaching dAz per second is given by exponential minus sigma e r to 0 to pi by 2 integration r is equal to 0 to infinite e to the power minus sigma t r phi r cos theta sin theta dr d theta d phi. To obtain expression for the number of neutrons passing per second in the negative z direction through a unit area, we divide the above expression by dAz, and this gives Jz is equal to sigma s by 4 pi integration phi is equal to 0 to 2 pi integration theta is equal to 0 to pi by 2 integration r is equal to 0 to infinite exponential minus sigma t phi r cos theta sin theta dr d theta. And this integral can be used to expand the unknown function phi r as per the assumption using Taylor series, as phi r is assumed to be a slowly varying function. So phi, which is a function of distance, is equal to phi 0 plus x del phi by del x which is phi by del y at phi equal to del phi by del z at z is equal to 0 plus so on so forth. For the subscript 0 indicates that phi and its derivatives are to be evaluated at the origin. So in spherical coordinates, you can have your x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, z is equal to r cos theta, and by inserting the terms containing cos phi and sin phi, will drop out. So the expression for Jz reduces to Jz is equal to sigma s by 4 pi integration r is equal to 0 to infinite integration theta is equal to 0 to pi by 2 integration phi is equal to 0 to 2 pi exponential minus sigma t phi 0 plus del phi by del z z is equal to 0 and z is equal to 0 r cos theta multiplied by cos theta sin theta dr d theta d phi. On simplification, we can get Jz is equal to sigma subscript s phi subscript 0 by 4 sigma subscript t plus sigma s by 6 sigma t square del phi by del z at z is equal to 0. So the number of neutrons moving per second in the positive z direction through a unit area in the xy plane, and your Jz plus is essentially the same as that of Jz minus. So the limits of integration on theta will change, and the expression for Jz plus is nothing but sigma s phi 0 by 4 sigma t minus sigma s by 6 sigma t square del phi by del z, where z is equal to 0. So the Z component of current density refers to the net flow of neutrons per unit area, so that Jz is equal to Jz plus minus Jz minus is equal to minus sigma s by 3 sigma t square del phi by del z at z is equal to 0. The other component of J at the origin are given by expressions similar to equation 13.15 as I discussed. That is Jz is equal to Jz plus minus Jz minus is equal to minus sigma s by 3 sigma square del phi by del z at z is equal to 0. So the other component of J at the origin are given by expressions similar to the equation but with z replaced by x and y. So your jx is equal to minus sigma s by 3 sigma t square del phi by del x at x is equal to 0. And your jy is equal to minus sigma s by 3 sigma t square del phi by del y at y is equal to 0. Is given by I x plus j cap plus jy plus k cap plus k cap jz. So Jz can be resolved into I cap Jx plus J cap Jy plus K cap Jz. Sigma s by 3 sigma t square grad phi. And it is nothing but we state that the current density vector is proportional to the negative gradient of the flux. The proportionality constant is called diffusion coefficient and is denoted by the symbol capital D. With this notation, this law can be expressed as J vector is equal to minus D grad phi, where D is equal to sigma s by 3 sigma t square. Then we will discuss the diffusion equation. So, Higgs law gives us a relation between the neutron flux and neutron current. We can obtain an equation involving the neutron flux using the equation of continuity. And we substitute the result content in equation and we can get del D grad phi is minus sigma a phi plus s is equal to del n by del t. For a homogeneous medium, D is constant. Then your first term, that is divergence of your d del phi is equal to d del square phi, but del square is the Laplacian operator. So all neutrons have been assumed to be of same energy or having same speed, monoenergetic electrons, and the flux phi is equal to NV, and you can write d del square phi minus sigma a phi plus s is equal to 1 by v del phi by del t, and it is nothing but the one-speed diffusion equation and is widely used in nuclear reactor theory. If the neutron flux is independent of time, the right-hand side will be 0, and the equation will be reduced to d del phi minus sigma a phi plus s is equal to 0, and this is known as steady-state monoenergetic diffusion equation. In mathematics, you can refer as scalar Helmholtz equation. For convenience, we can rewrite it as L square phi minus 1 by L square phi is equal to minus s by d, where L square is equal to d by sigma a, and L is equal to root over of d by sigma a, which is called diffusion length. So, this diffusion length term L appears often in reactor theory. And your d and sigma a have units of centimeter and centimeter inverse respectively, and L has units of centimeter. So, in one-speed approximation, the diffusion coefficient can be expressed in terms of macroscopic cross-sections as capital D is equal to 1 by 3 sigma t minus sigma s mu 0. Here, sigma t is the total cross-section or sum of absorption sigma a and scattering sigma s cross-sections, and mu 0 is the average cosine of the neutron scattering angle. So you can recognize that the quantity within the parameter within the parenthesis is transport cross-section sigma transport or sigma tr, and its reciprocal is known as transport mean free path. So your sigma t minus sigma s mu 0 is equal to sigma tr is equal to 1 by lambda tr, which is the mean free path. And you can express d as 1 by 3 sigma tr is equal to 1 by 3 lambda tr. For weakly observing medium, your sigma t may be replaced by sigma s. So now reduced to d is equal to 1 by 3 sigma s, 1 minus mu 0 is equal to lambda s by 3 multiplied by 1 minus mu 0. Your lambda s, nothing sigma s, scattered 1 and the extrapolation distance at the surface is presented in the slide. So your diffusion equation is a partial differential equation, and to solve it, we have to specify certain boundary conditions. For neutron flux to be physically acceptable, we expect phi to be real and non-negative. This is because negative or imaginary flux is unphysical and has no meaning. Moreover, flux must also be finite except at artificial singular points. So, in real physical situation, neutrons leak from the surface between the medium and the atmosphere. Fick's law and diffusion equation are not valid in the immediate vicinity of an interface between surfaces. However, it has been found that if the flux calculated from the diffusion equation is assumed to vanish at a small distance small d beyond the surface, the flux obtained by solving diffusion equation is very nearly equal to the exact flux in the interior of the medium. So you may argue that zero flux at a small distance d beyond the surface is non-physical. It is convenient. It is a convenient mathematical approximation that provides high degree of accuracy in estimating the flux inside the medium. Okay, so d is known as the extrapolation distance and is given by d is equal to 0.71 lambda tr. Well, lambda tr is the transport mean field path of the medium and is related to by the expression lambda tr is equal to 3 capital D. By combining the equations, we can have D is equal to 2.13 capital D. Measured value of D for non-gaseous materials are usually less than 1 centimeter or less. So, D is small compared to reactor dimension. So, while solving the diffusion equation, we can even assume that neutron flux vanishes at the actual surface of the system. In case where D is not negligible and we must establish a mathematical boundary for the problem. This boundary is referred to as extrapolated boundary, located at a distance small d from the real physical boundary. This boundary condition is referred to as the vacuum boundary conditions. This is typically imposed on systems where there is a medium having low density of neutrons in a region or at the edge of the system where few neutrons re-enter the region of interest. A typical example of such problem is in the air-filled annuls outside the reactor vessel. In such cases, the actual dimensions of the system increases by d. Consider the case depicted in the figure, planar sources at the origin. If the distance from the center of the diffusion media is small a, the distance to be extrapolated boundary will be a plus d, which is usually written as a plus d. So your phi a is equal to phi b, which is at the interface between two regions a and b. and your JN is equal to JBN, where phi and phi B are respectively the fluxes in region A and B evaluated at the interface, and JN, JBN are the normal components of the neutron current evaluated at the interface. So this is the interface boundary condition. Then multiplying and non-multiplying media. Okay. So in each fission at uranium 335 nucleus by thermal neutron, on an average 2 to 3 neutrons are produced. This means that systems containing fissile material like uranium 235, uranium 233, uranium 239, plutonium 239 produce additional neutron as a result of neutron absorption leading to fission. When your sigma F is not equal to 0, the source of neutron in the diffusion equation may arise. Fission depends as well as on the independent source. Such media are called multiplying media. Because of a large proportion of uranium-238 in natural uranium, which absorbs thermal neutrons and does not necessarily undergo fission, except by high energy neutrons, the fission cross section for this fissile material at low energies is essentially zero. So your sigma F is equal to 0. Media containing only fertile materials, that is uranium-238 and thorium-232, but not fissile materials, behave as non-multiplying media. In non-multiplying medium, the source S is determined only by the independent source, and the source term for a non-multiplying medium in diffusion equation is 0, except at the position of the neutron source. For convenience, usually the source is assumed to be situated in the center of coordinate system and freely diffused throughout the medium. Okay, so in the next class we shall discuss one spin neutron diffusion equation in a non-multiplying homogeneous infinite assembly. Okay, thank
Thank you,
you.
sir.
If you
Thank you,
have
sir.
any doubt, you can ask.